Hi folks, welcome to this short series where I try to give an intuitive explanation of covariance matrix adaptation evolution strategy, or CMAES. This first part is intended to be a gentle introduction to what evolution strategies are in general and what it means to quote-unquote adapt covariance matrix. I will be using a lot of material from this Otoro tutorial, which is a fantastic tutorial for intuitions, and I highly recommend that you check it out. But if you are already familiar with this content, then you can skip this first part. And after we've laid the foundation, we're going to dive a bit deeper and look at the formal CMAES specifications as given in this paper. There will be some math, but I plan to mostly stay on the intuition level and focus more on what the math mean and what are the motivations and how they relate to the aforementioned Otoro tutorial, instead of getting entangled with the derivations. So let's get started. So what is evolution strategy? Well, evolution strategy is a family of algorithms that generally follow the principle of survival of the fittest, which got its inspiration from the evolution in nature. There are many variants, but they usually go in the following loop. You generate a number of individuals as your population. You sort the population according to their fitness. You get a subset of the population that have high fitness, and you call them your so-called elites. And then you use the elites to produce individuals that will go into your next generation. This mu lambda notation you see on the upper left is a common notation used to categorize evolution strategies. Lambda here represents the number of individuals that you produce for each generation. Essentially the pop size, the population size, but it gets a bit more nuanced and hopefully it will become clear later. The mu here represents the number of elites, the parents that you use to produce those lambda individuals. So for example, you might be crossing over the top 5 individuals or top 10, and those 5, 10, those numbers are the mu. If it's mu plus lambda, then the new individuals that you produce go into your current population, which now contain individuals from both the old population and the old generation and the new generation. And the parents are essentially given a chance to compete with their children. On the contrary, if it's mu comma lambda, then upon producing the new generation, individuals from the old generation are simply discarded, regardless of their fitness. This might seem a bit counterintuitive at first, but then remember that animals in nature die of old age, regardless of how well they've been doing for this life. So this concept of discarding parents is not unfounded. And moreover, it is believed that discarding the parents will help evolution overcome local optima, which is actually one of the prime reasons that you might use evolution strategy in place of gradient-based methods. There needs to be a way to generate individuals from elite parents, and one way of doing so is through sampling from a normal distribution. Just a quick recap, a normal distribution is characterized by the mean and the standard deviation. And essentially, the further a value deviates from the mean in units of standard deviation, the less likely this value is to be sampled. And therefore, you have this little mountain-shaped probability distribution function with the highest sampling probability at the center, i.e. mean, and decreasing probability going either direction. This is for when x is just a scalar, but most likely you'll want to evolve multiple variables together, in which case you'll need to extend to the multivariate case of normal distribution. It's quite similar, except now the data points and the mean are both vectors, and in place of a standard deviation, you have the covariance matrix. Covariance matrix is a matrix arranged in such a way that the diagonal terms are the variances within each variable, from x1 to xn, whereas the off-diagonal terms are the covariances of variables with one another. With no variance, variance is just the square of standard deviation and measures how much does a variable fluctuate, and by extension it controls kind of how flat the distribution is along the direction of that one variable. On the other hand, covariance measures the association between the changes of two variables. So for example, if you have a large covariance between x1 and x2, then given an x1 value that is much larger than the mean of x1, you can kind of expect its corresponding x2 value to also be much larger than the mean of x2. Or if the covariance is 0 between x1 and x2, then you essentially cannot tell how large x2 is given just the value of x1, because they are not associated. I have prepared a simple visualization that will hopefully help with your understanding. This is a simple visualization of a two-variable multivariate normal distribution that is characterized by the zero mean and the covariance matrix as shown on the top right. This circle is a representation of how widely spread the distribution is, and it essentially consists of points that all have the same certain probability of being sampled. I think in this case it's 0.2. As you can see, if we increase one of the diagonal terms, i.e. a variance, it's going to stretch the distribution wider along that one direction. On the other hand, changing the covariance has the approximate effect of sharing the distribution. And as you can see, with a large covariance between x and y, it is more likely to sample points that have both large x and large y, or both small x and small y. And of course, if we're given a set of data points, we can also calculate the covariance matrix from this set of data points. And we do that according to the equation given here. The E symbol here stands for expectation, and for our purpose, we can just treat it as the average. So now this equation reads, we take a data point x, we subtract it by the mean of the data set m, and we then kind of do an outer product of the difference with itself. And notice that if m is the zero vector, i.e. if the data set is centered, then this equation just becomes this much easier expression here. So now we have all the necessary materials to build a simple evolution strategy out of multivariate normal distribution. And the loop goes as follows. So first, we generate lambda individuals by sampling from this normal distribution lambda times. Since we're just trying to start simple and not bother with how to update the covariance matrix, we're just going to keep it constant throughout evolution. Then we add those lambda new individuals to the population and sort the population according to their fitness as usual. And then we get the mu top fitness individuals and make them our elites. And then we update the mean of the normal distribution to be the average across all these elites. Notice that since these elites are expected to have higher fitness, the new mean is expected to be an improvement over the old mean, which is the whole reason why this whole thing works. I think it's going to become clear after we see a simple demo. In this simple demo, we are trying to target this region of high performance on the lower right. And the circle here, again, represents how widely spread our current distribution is, similar to what we just saw earlier in the covariance matrix demo. The green dots here represents the individuals that we just sampled from the current distribution. And now they turn yellow because they're just added to our population. In our case, since we have mu equal to 3, we are going to select the top 3 individuals in terms of fitness and make them our elites. And as you can see, we also update the mean of the distribution to the average across these 3 elites. But for simplicity, we do not change the covariance matrix just yet. Now we sample some new individuals. We add them to the population, but you can also see here that some of the individuals turn red. This is because they have low fitness and they are going to be discarded in the next iteration. I forgot to mention this step earlier, but strictly speaking, you do not need this step in order to make the algorithm work. It's just there to save you some issues with the memory. Because you can imagine, right? If we did not discard these individuals, we're going to have some individuals in this direction. But because we are using rank-based elites selection, the elites are still going to be these top 3 individuals in the lower right. So the elite selection is not affected, and by extension, the sampling is not affected. Just a few more iterations. Yeah, and as you can see, it pretty much hits the region of high performance. In this simple evolution strategy, we kept our covariance matrix constant and have the same variance for all our variables, which results in this roundy shaped distribution. But if you think about it, this is not really the best distribution for this problem, right? Because what we really want is an ellipse that biases the search along this direction. So something that looks like this, probably. Sorry for the bad drawing. And how can we accomplish that? And we should also remember that the algorithm does not have a global view on the fitness landscape as we do. And the only information it has are the individuals and their fitnesses. So how can it find out the distribution shape on its own, given such limited information? Well, imagine if you are in front of a vending machine and you do not know how the vending machine works, but you try pressing the button on the left and it doesn't give you anything. And you try pressing the button on the right and it gives you a can of cola. So even if you do not know how the vending machine works, there's still a reasonable course of action for you, which is to keep pressing the button on the right. It's kind of the same deal for the evolution. So if it generates an individual and this individual has high fitness, then it's kind of an indication that it should keep generating individuals along that direction. And which individuals have high fitness? The elites. And therefore, next we're going to see how we can use the elites to figure out the covariance matrix and to change the shape of our distribution. So this equation here shows a simple way of how we can adapt the covariance matrix from the elites. And again, we are just taking the difference with the mean and then doing an outer product with the transpose, and eventually just taking the average across all these elites, which all seems pretty normal. But notice that the mean here is not the mean from the current generation elites, which if it were, we would just be simply calculating the covariance matrix of the elite samples. But we do not want that. And instead, we want the covariance matrix of the steps of how we arrived from the previous mean to these new elite individuals. Because intuitively, we want to exploit that information, right? And we want to reproduce those steps of how we got from the previous mean to the elites. And for this reason, the mean we are using here is actually the mean from the previous generation. And by doing so, this difference is going to give us information about which direction do we want to explore. This other equation shows how to update the mean, and it's just the same as what we've been doing. This GIF on the right shows how it is supposed to work, but as we will see soon, this simple way of adapting the covariance matrix has its deficiencies, so we are not quite there yet. So this is an implementation of the idea, and let's see how it works. As you can see, it is successfully adapting the shape of the distribution. But it doesn't quite work, right? Because later into the evolution, the distribution just pretty much becomes very thin and doesn't allow much exploration in either direction. That's the first problem. And you might also spot a second problem, in that the shape of the distribution, the size of the distribution kind of shrinks a bit too quickly. And it's not hard to see why, because if at any point during evolution, the size of the distribution is shrunk, the elites that you sample from that distribution are likely going to be closer to one another. And as a result, the covariance matrix you calculate from these new elites is likely going to shrink the distribution even more. And the trend just kind of reinforces itself from now on. So this is just a quick summary for what we did in part 1, the pseudocodes and all. This part is the sampling, and these two are the equations we just saw in the previous slide. Except their order is swapped because we want the mean from the previous generation. And we saw this method has its flaws. So in the next part, we are going to look at the actual CMA yes and see how it addresses some of the problems we've seen so far. See you then.